tell to us about the verified just-in-time compilation.
Yeah. Can you hear me? Okay. So today we'll present my work, our ongoing COC development about formal verification of just-in-time compilation. So this is a work with Sandrine Blasi and David Pichardy. And I'm sure many of you are familiar with formally verified static compilation, and there are many projects such as ComCert or KKML, for instance, that are interested in formally verifying static compilation. And in such a setting, you start with a source program, and then you statically feed it to your compiler, and then the compiler will produce some native programs that can then be executed independently of the compiler, for instance. So in this setting, compilation happens statically, and the code is not self-modifying, for instance. It will just be run as is. And yeah, that's the setting that you know. Now, if you want to prove a static compiler correct, what you have to do usually is find a way to prove that any behavior of your native program, your compiled program, actually matches the behavior of your source program. So if you show that, then you prove that your compiler preserved the behaviors and did not introduce any bugs, for instance. Now, what about just-in-time compilation? So there are many different kinds of JITs, but in general, most modern JITs start with interpretation, for instance. So your execution, this little arrow on the right, starts with interpreting your source code, for instance. But then, in the middle of the execution, you can decide to dynamically call a compiler to compile one function, for instance. So what you're going to do is dynamically call this thing and replace one of your functions in your source code with the optimized function. So in a way, this is a bit of a self-modifying code. And so the execution is already a bit different than in the static case, because you already have both interpretation and execution of optimized code. And then some modern JIT compilers, on top of that, decide suddenly in the middle of the execution of an optimized function to perform what we call on-stack replacement and go back to the interpreter and to interpreting source code. So this is, of course, different from the static setting, and this is what we want to formally verify. So our verification challenge somehow is to find a way to relate this execution that interleaves a lot of things, like interpretation, execution of optimized code, to an original execution of the source program according to its semantics. So just-in-time compilers, as I've said, there are many different kinds of JITs, but they are broadly used today, and you're probably using one in your web browser, for instance. But in the most general sense, JIT compilers usually interleave interpretation, dynamic compiling, and execution of this optimized code. So here are a few examples of JIT compilers, like V8 or PyPy for Python, that you may know. And one technique that is really specific to just-in-time compilation and that you don't usually see in static compilers is exploiting dynamic information. So basically, because you are doing your compilation dynamically, you have access to some dynamic information about the execution of your program that you could not have had statically. And so if during your first interpretation phase you try to record some of that information, then you can use that later to try to speculate on the future behavior of your program when you do optimization. And this is called speculative optimizations, and it's very characteristic of modern JIT compilers. So what you do is that whenever you are interpreting, you're also running profilers that will record stuff about your execution. And when you decide to optimize, you will create a specialized version of your function that uses this dynamic information. So let's look maybe at a simple example. So let's imagine that we have a function f that is repeatedly calling a function g. And this function g is just doing some basic sum and product to fill up some arrays. And let's imagine that we are in a dynamically typed language. So in this setting, the plus and times operator are actually polymorphic functions. And they are not so efficient because each time you interpret them, you need to check the types of the arguments to decide which procedure to actually call when you do the sum or the product. And if you call f, and then you will call repeatedly g, and you see that g is always called with, for instance, integer arguments, then you might think that it's a bit redundant to always check for the type of the arguments. You would like to say, okay, I know that my function will probably be called for integers. And so this is what you can do with speculative optimizations. So what you will do is generate the following code for G. So you will speculate that, okay, next iteration, I'm sure that A will be also an integer, and array of I will also be. And then you can already decide which procedure to call. And so it allows you to make some specialization and to be a bit more efficient. But you can speculate on a lot of things, not only types. So you can also speculate on values, for instance. So you can speculate that B is equal to 0, and then you get more simplifications. So this is the main principle of speculative optimizations. And of course, because this is speculation, you have no guarantees that the next iteration will also follow this rule. So you need to find a way to go back to the unoptimized version in case your speculation is just not true. So to wrap it up with JITs, let's look at the last example of JIT execution. So once again, we have a function f that is repeatedly calling a function g. And so when you start your JIT, the first time you're going to call g, you're just going to interpret it, right? You call the interpreter, and alongside it, you're going to call your profiler to record some information. So maybe the second time you will do it as well. And when it's time to call g for a third time, for instance, you know that, okay, maybe g is a hot function that would be worth optimizing. So you decide to call your dynamic compiler, and you create a new version for G that you insert into your program. So this is this version gopt. And in this function gopt, you may add some speculation about what you've seen previously in the previous executions of G. So now when you need to call G, you can simply execute the optimized version, right? And of course, if at some point in the middle of the execution of gopt, the speculation fails, then right in the middle of it, you perform on-stack replacement, and you go back to the original version of G. And so yeah, this is how a program can get executed in a JIT. So the takeaway is that you need to interleave this execution of optimized and non-optimized code. You need to keep several versions of each function, for instance, this G and this gopt. And you need, of course, instructions or procedures to make the speculation and de-optimize and restore the environment if needed. So there have been, of course, some previous work on formalization of just-in-time compilers and just-in-time techniques. So one first work that we know of is verified just-in-time compiler for x86. So this is a translation from a stack-based bytecode to x86, and it's fully verified with HOL4. So this is very interesting. However, there is no optimization being made at all by the compiler. So it's not very characteristic of a modern JIT compiler. And of course, because there is no optimization, there is no speculative optimizations. So we want something a bit more realistic today. Another interesting work is the work on JIT-K, which is an in-kernel interpreter for packet filtering language. And it's actually interfaced with Concert, for instance. But in Concert, there is no speculative optimizations. There is no self-modifying code. Once you have compiled your code, you can just run it as is. So this is not exactly what we want to do. Now, an even more interesting work for us is the work on Sourire, which was submitted at POPL 2 years ago. So Sourire is an intermediate representation that is made to handle speculative optimizations. So there is a new instruction, for instance, that will handle both speculation and the optimizations. And in this paper, there is already some proof inside, some paper proofs about speculative optimization, which is great. And there is no mechanized proof, so you have, and also you have no way to execute it directly, but there is already some insight. And maybe to make clear what the scope of our work is, you can look at a day in the life of a function in a modern JIT compiler. So a function will usually start as some source code that can be interpreted, for instance. And when we decide that it's time to compile it, the function will first be translated into a JIT intermediate representation. And this representation should have instructions to handle speculation and the optimization. Now, in this representation, we can make this big loop of a first compilation phase that is a middle-end phase that actually deals with speculation. So you can, for instance, insert new speculation points. You can move around speculation, make speculation stronger, and so on and so on. And once you're done with it, you go to the second compilation phase where you translate it, for instance, to native code so you can run it really efficiently. Now, what we are interested in so far is actually the JIT middle end, so the part that handles speculative optimizations. So we focus on this JIT middle end, and what is different from Surya, for instance, is that we also are interested in how proving the JIT middle end interacts with the other components of the JIT, like interpretation, profiling, and so on. And to do so, we are developing a COC prototype of a JIT middle end. So it's mostly written in COC, and we wanted to have a realistic architecture that is really typical of modern JIT compilers, so with optimization, interpretation, and speculation. We wanted to have modular correctness proof, of course. We want each optimization pass to be proved separately, and we would like, for instance, the correctness proof of the interpreter to have nothing to do with the correctness proof of an optimization, for instance. And doing it in COC, we can actually extract it and then execute it, which is really good. And we also have a JIT correctness theorem, which, as we will see, will be a bit different from what you have in a static compiler case. So we have implemented a few of these components, a few optimization about speculations, and we have proof for some of it, and some are in progress. And one interesting result so far maybe is that the profiler does not need any proof of correctness for the overall JIT correctness to be preserved. So actually what your profiler is doing is only impacting performance and not correctness, so we need less proof to do. So let's go back to how can we formally prove correct JIT compiler. So in the static case, as you may know, in ComSearch, for instance, the kind of theorem that we want is to say that if compilation succeeds and the original program had actually a behavior, was safe in that case, then any behavior of the compiled program actually matches a behavior of the source program. And so this is the kind of theorem that you can find in ComSearch. So the first line says that, okay, compilation succeeded and P was compiled into TP, for instance. And then you have what we call a backward simulation between the semantics of the original program P and the semantics of the compiled program TP. Now, this exact theorem we could not use in a JIT setting, right? Because, for instance, we don't know statically which program is going to be executed. We don't know this TP because we don't know which optimizations are going to be made and what will happen in the JIT. So we can't exactly write this thing, but we would like some kind of similar methodology to prove the correctness of our JITs. So let's go back to backward simulation that you just saw in the previous theorem. So to prove a backward simulation in ComSearch, for instance, what you have to do first is find a matching relation between the semantic states of your original program and the semantic states of your compiled program. And this intuitively means that you are at the same point in the execution of both programs. And then to prove the backward simulation, you have to prove that each time the compiled program takes a step with some behavior E, with some behavior that you can observe E, then there exists a matching set of steps in your original program that has the same observational behavior. And so this is the backward simulation, and if you prove that, then you can do it once more and prove that every execution of your compiled program matches actually an execution of your original program. However, if we want to use that in a JIT, maybe you can see that this program on the right, TP, does not change, right? In a static setting, only the semantic state changes when you execute your program. But in a JIT, when your small step is actually an optimizing step, then your program will change because you will, for instance, add a new version into your program. So maybe the most obvious thing to do, and what we did, is put the program that is dynamically evolving into the semantic state. And then what you have to do is find a matching relation between semantic state of the original program and this big JIT state that contains both the program and the semantic state. And if you have this relation, then you can prove something that really looks like a backward simulation in a static compiler case. So this is the kind of theorems that we can have in our JIT development. And basically, it says that, okay, if you have your input program P on the left, which is the original one without any speculation whatsoever, and if you have a JIT state that is matched with a semantic original state S, then whenever the JIT makes some progress with some event E, then you can find also a set of steps in the original program that matches this behavior and that is also matched, with your new JIT state. So by doing that, you also prove that your behavior is preserved by the JIT compiler and the entire JIT. Now we also have this stuttering case that is also present in static compilers, but is especially interesting now because, for instance, when you do an optimization step, you haven't made any progress in your execution, right? You're still matched with the same semantic state of the original program. So in that case, we have to prove that there exists some kind of well-formed decreasing order to prevent the JIT from just optimizing to no end and never resuming execution. So this is the kind of theorem that we want to prove in a JIT compiler. And now that we know what we want to prove exactly, we can try to implement it and find an intermediate representation to handle speculation. So of course, we were inspired by the Sourire papers that I presented earlier, and also we were inspired by Concert RTL, Register Transfer Language. So our language really is a lot like RTL, but with this new instruction assume from Sourire that I will explain a bit later on. We also have, of course, a mechanism to handle function versions because when we de-optimize, we need to keep several versions of the same function. Of course, because we are only interested in a middle end of a JIT right now, this is the only language of our JIT, which means that our dynamic compilation is actually dynamic optimization, and our optimized functions are also getting interpreted right now. And of course, the original program does not have any speculation. You insert them during your middle end. Now, this assume instruction that we are inserting was shown in Sourire to be both precise and concise enough to handle speculation and the optimization. So in such an instruction that you can have in your code now, in your new representation, you first have an expression list which represents exactly what you're speculating on. Then you have what we call the optimization target, which is more or less a PC of where you want to go back to in case of the optimization. And then the two last things are used to restore the environment of the original program. So for instance, we have this varmap thing that restores the register environment. And then in some cases, it has been shown that the original environment had more call frames in its stack. So you need something to re-synthesize some stack frames into your stack. And so this instruction is good enough for speculative optimization. So for instance, if you encounter such an instruction in your code, what you're going to do is first test if the list of expression holds. And if it does, then you can go on in the execution of your specialized version. And if it doesn't, however, you will go back to function f version v1 label 5, and you will also restore the environment. So in that case, you will put value 10 in register A. So once we have this intermediate representation, we can start adding a few optimization passes in our middle end. And in many modern JIT compilers, the first optimizing pass is not really optimizing, but rather inserting speculation points. So first, what you want to do is add the point where we're going to do speculation and then decide if we need to de-optimize or not. So we're doing this quite simply on just speculating on the value of function arguments. So for instance, such a function can be transformed into this function with a simple instruction assume. So we are assuming, for instance, that R2 will be 10 because, I don't know, in the previous executions, R2 was always 10, so now we think it's time to speculate on that. And of course, if this fails, we need to go back to your original version at the first line. So this is what we do to insert speculation. And now, because you see, we're only inserting one line, not modifying the rest, we need to actually infer some information from this speculation. And this is what our constant propagation does. So for instance, if you had a program with some speculation and you speculated that register R2 will be 0, then you want, when you transform your program, that in the end you have made optimizations where R2 was removed. So this is what we do with constant propagation. So we just adapted the standard static compiler optimization to do so. And to verify it, we can actually already reuse a fixed point solver library from Concert. We were also interested in function inlining because this is such an optimization where you need to synthesize stack frames when you have to de-optimize. So we implemented inlining, which simply replaces a function call by its code. And there is this small particularity: whenever you are inlining a function that contains speculation, you have to also modify your assume instructions to synthesize the correct frame when you want to de-optimize. So this is the kind of transformation that we make and that we want to prove correct. Now that we have some optimization passes, what we want to do is find a way to modularly verify them in such a way that we can derive the overall backward simulation that we presented earlier, right? And what we have shown is that we can reuse a methodology that was also used in ComCert, for instance, which is proving each optimization pass with a forward simulation. So a forward simulation is kind of like a backward simulation, but in the other direction. And there is a very, where you reason about behaviors of your source program and deduce behaviors of your compiled programs. And there is a useful theorem in ComCert that says that under certain hypothesis, if you have a forward simulation, you also have a backward simulation. And this is usually a bit easier to prove. So this is what we want to reuse. And what we have proved is that if for each optimization pass we can actually prove a backward simulation, like in this optimization correctness theorem, then we can prove the big modified backward simulations of the JIT. And this backward simulation of each optimization pass can as well be obtained by a forward simulation and then applying the same kind of theorem. So in conclusion, what we have now is a coq model of a realistic JIT architecture. The architecture itself is much more realistic than previous work because we are doing this kind of interleaving, profiling, interpreting, and so on. And this prototype can actually be executed and run on a simple language. And we have modified the notion of backward simulation to really fit into the JIT setting. And now we can prove that if you want to add an optimization pass, the takeaway is that it looks very much like adding an optimization pass in a static compiler, for instance. So before in a static compiler, what you would do is find a way to relate native executions to source execution. And now the theorem that you need to prove is a backward simulation between this program and this program every time you want to add an optimization pass into your JIT middle end. So the takeaway is that we are able to reuse most of the methodology of proving optimization passes and integrate that into a broader JIT correctness theorem. Finally, for further works, because this is an ongoing coq development, we would be very much interested in implementing and verifying the Sourire transparency invariant. So this was introduced in Sourire, and basically it allows you a much more precise handling of speculations. So you can move around your assume instructions a bit more freely and merge them and move them and so on. So this would be interesting. And of course, we have been interested in the middle end part of the dynamic compilation, and it would be natural to now get interested in the back-end compilation phase. So at first sight, it seems like the actual machinery, the actual translation of ComCert that translate a program from RTL, for instance, to assembly is enough to deal with what we are doing now. But the specification doesn't really suit our needs because, for instance, ComCert is compiling entire programs, and what we want to do also with the compiled code is go back to the JIT that just called it in case we want to optimize some more, for instance. So yes, thank you for your attention.
Okay, so we have some time for questions.
So among other applications, there is also the compilation in debug mode, where you do add marks in the code.
What do you mean by that? Can you refer?
When you use GDB or you do a compilation to be able to use a debugger, you need to modify the code also in a way. Would that be related, or?
I mean, for the dynamic part, maybe, but for things that are really JIT specific, like speculative optimization, I don't think so, for instance.
Other questions?
ComCert's backward simulations, as far as I recall, they are parameterized by the programs and the program syntax and by the program states. Do you obtain your JIT backwards compilation by just instantiating the state with a tuple of program state and programs and instantiating the programs with units?
Okay, I think I see what you mean. You're talking about the backward simulation for each optimization path, or the?
No, I want to reuse the definition of backward simulations in ComCert. And since it's parameterized by the program states and the programs, my suggestion is to instantiate it in a funny way.
Oh.
So you're going to instantiate the states with a tuple of
okay, so it looks at what I'm doing. In practice, it's a bit, you need to add a little bit more stuff in it. For instance, your dynamically evolving simulation relation. So I think it's not just as simple as instantiating it on a tuple.
Okay, so there is some more complexity. Thanks.
Yeah, also, you know, in your backward simulation, you're not requiring, I mean, in a JIT setting, what you want is optimization to never fail, because you don't want the JIT to crash if the original program was not crashing, right? So you need to incorporate that also in your notion of backward simulation, because if the original program has a behavior, you need the JIT compiler to also have one.
Other questions? I had a question. Can you go back to the explanation about the subtlety with the functional inlining? So there's some issue with nested assumes. Is that the?
Yeah. No, not nested assume. Just if your inline code has an assume, you have to go back. I actually maybe have. Okay. So if you have this function f, this function g, and then you decide to optimize dynamically your function f. So you have this new version v2 that has an assume instruction that de-optimize back to version v1, right? And if you decide to inline the version v2 of f inside of g, so you will have an assume instruction that goes back to v1. But if you're executing your inline code and you de-optimize inside of this v2 of g, so you go back to v1 of f, but then you have to go back actually in the original version of g as well. So this is this little dashed line, which does not appear as a dashed line at all. This bottom arrow is actually what we are adding in the assume instruction.
Okay, thank you. Other questions? Oh yeah, I have one more. So right now the JIT is implemented in, I mean, you're going to extract from coq to OCaml.
Exactly.
So are you concerned about the performance of?
Okay, so far it's more like an executable model of an architecture.
Okay.
So performance is not right now the, what we are looking at, but yeah, I also wonder what would be the overhead of doing it in such a way, because the compilation is dynamic. So yeah.
I think I'm still a bit confused about something. So all of these JIT optimizations, are they Galena functions or are they something in the actual language?
As a what?
So the optimizations that the Git executes, are those written in Galena or are they written in RTL?
They're written in Galena.
So how does that work with abstraction? Because if you extract, then how do you actually execute the program then? So if you want to execute the RTL program, then at some points it needs to call the optimizer. So then somehow RTL needs to interface with OCaml or so?
I mean, right now with only one language, you don't have this kind of interface issue. But yeah, if you're mixing really the two languages.
But wait, there are two languages. There's the optimizer, which is written in OCaml.
Oh yeah.
And there is the RTL program. So if you would want to actually execute the RTL program, then it needs to interface, then it needs to call Galena functions. So how would you imagine executing this?
Okay, I think the whole runtime so far is like an OCaml function that has been extracted. So you need to see the JIT like as a big interpreter that either decides to interpret, and the interpreter is also an extracted Galena function, or optimize, which is also an extracted Galena function.
Oh, so the runtime of RTL is just an extracted function?
Yeah, as well.
Okay, I see now. Is that, by the way, a realistic assumption?
I mean, so far, if we are only concerned with a JIT middle end, it's fine. If you want then to extract it and use backend compilation, then you will have this kind of issue, yes. But I think for now it's a bit orthogonal.
Yeah, I see that, but I was just wondering.
Oh, but?
I see that it is orthogonal at this point, but I was just curious.
Yeah, me as well.
Okay, I think that's all the time we have. If there are no more questions, let's thank the speaker.